All right, in today's video, we're going to be talking about section 2.2. We're going to be talking about polynomial functions of higher degree. Of course, we just got done reviewing quadratics, which are polynomials. They are polynomials of second degree. And I guess chapter 1, we did polynomials because we did linear, which are polynomials of the first degree. So now we're going to just kind of talk about everything polynomial at this point. So first of all, at the top of the screen, you'll see what I've written as the general description, kind of general formula of a polynomial function. It looks kind of intimidating, but if you take a quick look at this, you'll see that all we have is we have different terms. So we have term 1, we have term 2, skip all the way, we've got the term, we've got a little term, and we've got a term. So each term has an x to a power, so this could be like x to the n, right? So maybe n is 5, so it's x to the 5th power. Then this is x to the n minus 1, so we go down 1. So that'd be x to the 4th, etc. All the way you get down to x squared, x to the 1st, and then no x. There's your constant term. The a sub n and the a sub n minus 1, those are just describing the coefficients that go with the x to the nth, so the nth, the first term, right? So this is, if this is x to the 5th, then this is a to the 5th, telling you it's the coefficient on the term that is x to the 5th. Long story short, it looks more intimidating than it is. It is really just some version of, I'll just make one up, 5x to the 4th plus 3x to the 3rd minus 2x squared plus 7x minus 5. My n goes from 5 to 4 all the way down to no power, and then each of them have a coefficient that goes along with it. Polynomial. That's it. Describe the basic look of a polynomial graph. So there's two main things I want you to kind of get across from this. So a polynomial graph, if I just ask you to sketch a generic one, you might show me something that looks like this. So what do we know to be true about them? Well, there's nothing weird going on. There's no breaks. There's no what we would call discontinuities, meaning we're not cruising along here and then suddenly we have like an asymptote, right? We're not going to run across that because my domain, as we know, is all real numbers, because I can plug anything I want in and I'll get an answer. I've got no square roots or zeros that would limit my domain in any way. So we have no weird breaks. We're certainly not going to be coming along and then like have an open circle and drop down here or anything like that. So the first thing we would say is that it's continuous. And then the other thing to talk about is that unlike, say, maybe an absolute value graph, which you're cruising along and then you make a hard turn, right? There's no like we're going one way and then immediately we snap the other direction. On a polynomial, our turns are very gradual. Like we're going up, we kind of slow down going up, we peak out, and then we start coming back down, and then we're going to turn again. And so the way we would talk about that is it's like smooth, gradual turns. So usually what we talk about polynomial graphs, we talk about them being smooth and continuous. Okay, gentle turns, no weird breaks. All right, so today what we're going to do is just kind of review some of the basic properties of how we can sketch a graph of a higher polynomial. So the first thing to do is remember that the graphs behave kind of very predictably. So what I've asked you to do on this one is to take a moment and just kind of graph each of these. Looks like we've got 6 functions. So go ahead and pause the video and get those graphed. All right, we have x squared down pretty well. So the red here, that's x squared. We know we go up 1 and then 3 and then 5 from point to point. A couple of you know it. You go up 1 and then 4 and then 9. That's fine. I just don't like to recount all the way to 9 when I've already counted up to 4. So we have that one. X to the 4th is going to look very similar. We got 0 is 0. 1 to the 4th is 1. And then 2 to the 4th is 16. There's 4. That's 9. 10, 11, 12, 13, 14, 15. There's 16. And so at -2, we're also up here at 16. And so we know this, ooh, that's ugly. Let's try that again. So we know this graph looks like this. And then, of course, x to the 6th, 2 to the 6th is like 64 or something. And so I can't even get that on the graph other than to say that at the beginning, we still have 0, 0, we have 1, 1. I'd like to take, and let's just zoom in real close on that, okay? So if I grabbed that and I zoomed in real close, and I focused on, 1 to 1 right here, then what I know is that my red graph, my x squared graph, we all have the same 2 points. And my x squared graph will say it looks something like this. Well, we know that the x to the 4th graph is going to be bigger than the red graph, but it's not going to be bigger than it between 0 and 1. Because if we think about a number like plugging in 1/2 squared, 1/2 squared is 1/4. That's pretty small. But if I plug in 1/2 here, I'm going to get 1/16. That's even smaller. So the x to the 4th, while it may be bigger once I cross 1, before I cross 1, it's actually going to be below the graph of x squared. And if I look at then x to the 6th, it's going to be the biggest of all of them, but not between 0 and 1. It's actually going to be the smallest because you're going to be at 1/64th at a half. And so we're going to be in here really small. And then we meet up here at 1, and then it just outgrows everything from there. So not a big deal, but I just want you to realize that there is some very specific detail in here we should think about at times, and it would be inappropriate to say that h of x is always on top of f of x. It mostly is, but not between -1 and +1. On those areas, it's going to be smaller. All right, let's get rid of that. And let's move over to the other ones, the odd ones. So let's go ahead and I'll graph this one in red. So this is linear. We got that down pretty good, I'm sure. Let's go with x cubed. We share 0, 0. We share 1, 1 again. We share -1, -1. But then I'm going to be at 2. I'm going to be at 8. 1, 2, 3, 4, 5, 6, 7, 8. And 1, 2, 3, 4, 5, 6, 7, 8. And once again, x cubed is going to be bigger than x for sure, but not between -1 and +1. And we can see that right there even without zooming in. Right? We're actually below that line. And then so x to the 5th is going to do very similar, except it's going to be 2 to the 5th. So by 2, I'm way up at 32 off the graph, but I am still crossing through the point at 1, 0, and -1. But once again, it's going to come down, be above, but below, it's going to cross below these and look like this. So if we zoomed in there, again, we would see that the green one is going to be the lowest and look more like this. And the blue one is going to be more like this. And the red one is going to be obviously like this. So same thing. The green one is always bigger than the blue and the red, but not between 0 and -1. And then the order is reversed. Okay, but the main takeaway here is we want to come up with basically a rule. And here's the rule. If the degree of your polynomial, and the degree, if you remember, is the highest degree, the highest power in the polynomial, so we look at the biggest power, if your degree of the polynomial is even, then, give myself a little more room here. What we would say is we're going to talk about the end behavior. So what's the general look of the graph? We don't know what's maybe happening in the middle, but what's happening as we get far enough out to the left and to the right? And the answer is, if it's even, they're both going up. So we would say as x goes to infinity, f of x, or y, goes to infinity. So x gets bigger, y gets bigger. As x goes to negative infinity, so now as I move to the left, x gets smaller, what are my y's doing? They're still going up to infinity. And if we come over here and look at a degree of the polynomial, is odd, what do we see happening? As x goes to infinity, y goes to infinity. And as x goes to negative infinity, y also goes to negative infinity. So in other words, as I go to the right, x gets bigger, y gets bigger. As I go to the left, so x is getting smaller, y is getting smaller. All right. Now, the piece of this that we need to include is the leading coefficient, because we know that if you put a negative out front of an x squared, it's not going to be what we just described, right? If I put a negative, it's going to reflect it over the axis, and now we'll do exactly the opposite. And so we can set up a whole new rule for this and make a whole page of notes that if the leading coefficient is positive, then it's this. But what we should just remember is that it reflects it. And then we need to have that show up in our description. So I think we can handle that without spending more time. So let's just do a practice. 5 practice. Use the degree of the polynomial function and the leading coefficient to tell us about the end behavior. So I'm just going to make a quick note. My degree on this first one is odd. And my leading coefficient is positive. So this one's just going to behave as I would expect it to. As x goes to infinity, so does y. Go to the right, it goes up. As x goes to negative infinity, so x goes to the left, y goes down. The graph looks some version of this. Now let's be really clear. I have no idea what's going on here in the middle. Okay, it could be going up and down, but eventually it's going to end up going up and end up going down. And that's all we're talking about when we talk about end behavior. All right, so part B, we have degree is odd, it's 5. And the leading coefficient, don't know why I use a cursive one, leading coefficient, too lazy to spell that out, would be 2, right? And so it's a positive. So this one's going to be exact same answer as before. As x goes to infinity, y goes to infinity. So that's, I'm going up to the right. And as x goes to negative infinity, y is going down. No idea what's going on in the middle, but eventually I know it's going up and down. Okay, next up, now my degree is odd still. It's 5 still. And now my leading coefficient in this case is what? -2. So the leading coefficient is negative. So now I know this graph is going to be reflected of what I would expect. So now I know instead of going up, it's going to go down. And since it's odd, we go opposite directions. So I should be looking at this. As x goes to infinity, y is now going down, negative infinity. X goes to the left, negative infinity. Y is now going up to positive infinity. My degree is even, and my leading coefficient is negative. So now, instead of going up and up, I'm actually going to reflect over and go down and down. So, as x goes to infinity, y is going down, and x goes to the left, y is going down. All right, and on this one, I have not written in standard form, and so we just have to realize that my degree is 4, so that is even, and my leading coefficient is not positive 4, right? It's whatever is on the highest degree term, so that would be negative because it's a negative 2. And so as x goes to infinity, we're now going down. So this is an x to the 4th graph. I don't know what's going on in the middle, but eventually it's going to go down on both ends. Could be doing all kinds of stuff, but in the middle, don't know. On the ends, I do. So as x goes to infinity, y goes down. And as x goes to negative infinity, the left, y goes down as well. Okay, let's keep going. All right, let's kind of review this statement here. This is a very important statement. It ties together lots of things. Finding zeros of polynomial functions. So when we're talking about finding zeros, we're talking about lots of things could stand in for that question, and that's what this little statement's about here. So let's see what we have. If f of x is a polynomial function, so visualize a random polynomial in your head, and a is a real number, and f of a equals 0. So that's telling me I plug in some number in a polynomial and I get a y value of 0. So in other words, what all is that telling me? So I've got some random polynomial functions doing its thing. And here at this a value, right, f of a, I get 0. So the output is 0. So that tells me lots of things. Number one, it tells me that a is a 0 of the function, right? That's the basic thing that it tells me. You plug in a, you get an output of 0. That means a is a 0. We also know that x equals a is a solution to the polynomial function f of x equals 0. So there's the, hey, let's graph it version. It's a 0. But we also know that if you were asked the question, hey, when does this equal 0? Then a is the answer. Again, almost exactly the same thing. But we also know that x minus a is a factor, okay? Because think about how we solve quadratics, right? If we factored our quadratic function into two different factors, and one of those factors happened to be x minus a, then we would set x minus a equal to 0, and I'd get x equals a is a 0. So if x equals a is a 0, which we've already established, then we know it came from a factor of x minus a. Okay? And then finally, graphically speaking, we know that that's also known as an x-intercept. So a0 is the x-intercept of the graph. So all of that is pretty synonymous. There's some, why does one time you answer this way versus another? Might be some semantic issues, but in general, they all mean the same thing. So example 2, find all real zeros and sketch a graph, including the correct shape. In other words, smooth, continuous, no hard turns, end behavior, and intercepts. So let's get all of that accurate. All right, so the first thing I want to know is I want to find all the zeros. Well, I know to find a 0, we set the function equal to 0. So I need to know when is f of x equal to 0. So I'm going to say 0 equals negative x cubed plus 4x. I'm going to factor out an x, and in fact, I might factor out a negative x. It's probably not going to matter that much, but I don't really like having my first term negative. So I'm going to factor out a negative, and that gives me x squared minus 4. And I know that that factors further into x plus 2 and x minus 2. So I know that the zeros are x equals 0, right? Because now I'm just going to go negative x equals 0 and solve, or x plus 2 equals 0 and solve, or x minus 2 equals 0 and solve. So I get 0, negative 2, and positive 2. So now let's sketch this with what I know. So what do I know? I know my end behavior. It's an odd function, but with a negative coefficient. So I'm going to go, let's do this. As x goes to infinity, y goes down. As x goes to negative infinity, y is going up. I've got my zeros. My y-intercept, that's when I plug in 0, and so I get the point 0, 0. And so let's put all that on a graph. My known points, I've got 0, 0, I've got positive 2, and I've got negative 2. I'm going to label these. And that's, of course, 0, 0. I'm going to get that out of the way here. And then in behavior. So I'm going down, I come up, I cross through again, I come up, and I end going up. Now, there's things I don't know and I'm not going to worry about. I'm not worried about how tall it is right there or how low it is right there. I know there is a maximum and I know there is a relative minimum, but I'm not going to worry about their location. Because honestly, I don't have the mathematical tools yet to answer that question. I could use a graphing calculator, I could guess and check, but there is a better way in calculus that you'll eventually learn on how to find that high point and that low point. But for us, it would be more of a guess and check or have the calculator do it for us activity. So we usually just sort of fake that part, but we get everything else accurate. And that's why you'll notice I did not use graph paper, because I wasn't worried about the scale, because I don't know what this is. This could go all the way to 100 for all I know. But I know that this general shape is correct. And that's the level that we need for polynomials. All right, example 3. Let's just kind of repeat that and find all the zeros and then sketch the function. All right, so you've hopefully tried this already on your own. So I want to know what the zeros are. So I'm going to set the function equal to 0. I can factor an x out. And hopefully I can factor this, because I really don't want to do anything. I'm getting tired. I don't want to do quadratic formula or even completing the square. Looks like 2 and 1 will work out just fine. Negative 2, positive 1. So I know that x has to equal 0, or x minus 2 has to equal 0, or x plus 1 has to equal 0. Or in other words, my zeros are x equals 0, negative 1, and positive 2. My end behavior, as x goes to infinity, this is a cubic graph, it's got a positive leading coefficient, so y is going up. And on the other side, going to the left, y is going down. My y-intercept, I already know it. That's going to be when f of, whatever f of 0 is. But we can already know that f of 0 is 0, and I knew that because one of my zeros was 0. So in other words, one of my zeros was already passing through the origin, which is, what the y-intercept is. All right, I think I have what I need. Let's put it on a graph and make sure it makes sense. All right, my zeros are at 0, at positive 2, and negative 1. So I'm going to label my zeros, label the y-intercept if it was separate, and then just make sure the rest of it matches what we know. So I know I'm starting going up. I'm going to smooth curve, turn it. I'm going to smooth curve, bring it down, and it should look something like this. Once again, not really focusing or worrying about how high or how low. Okay, I think that about covers that one. Let's jump over and do B. I'm going to find the zeros. Oops, that's a negative. Negative 2x to the fourth plus 2x squared. I'm going to factor out a negative 2 and an x squared. And that's going to give me an x squared minus 1, I think. I'm going to check my math. Negative makes negative, 2x to the fourth, positive 2x squared looks good. That factors further as the difference of two squares. All right, so I have zeros when negative 2x squared equals 0, or x plus 1 equals 0, or x minus 1 equals 0. So in other words, I have zeros at 0, negative 1, and positive 1. End behavior. Is going to be going down on both. So as x goes to the right, positive infinity, y is going down. X goes to the left, y is going down. And so I go put it all on a graph. And I've got 1, I've got 0, I've got negative 1, and I go to graph it. I'm going down on both sides, right? So I'm going to be down, I come up, I come down, I go up. Wait a minute, something's wrong. Let's see what's going on. So it's an even function. They're either both going up, nope, both going down. So I definitely have to be going down here. I have zeros here, here, and here. That's all great. I got my zeros. So I have to go up, I have to go down, I have to go up. I'm above. Can I come back down? The answer would be no, because I don't have any more zeros. There's no 0 there. So something is going on here. So we did not make an error, but we do have an interpretation of something we need to fix. So let's kind of get rid of all this stuff that's not needed. And what's going to make sense of this? So here's what I want to show you here. Let's go back and look at our factors. Let's look at this line right here. This is x minus 1 to the first power. This is x plus 1 to the first power. This is x squared. That's to the second power. So what we need to do is consider a little thing, which maybe most of you remember, is called the multiplicity, which is really just a question saying how many times does that 0 appear, or how many times does the factor appear that caused that 0? And what we care about is whether it's an even or odd multiplicity. And if it's an odd multiplicity, it's going to behave more or less as we expect. It's going to just pass through like we tried to do a second ago. And like we see on part A, notice this is x plus 1 to the first, x minus 2 to the first, and x to the first. And what we do? We passed through them. Okay? So what's going on here is we have an even multiplicity, right? So I have 2, I have 1, and I have 1. Or more importantly, I have even, odd, and odd. So basically what to know is at each 0, it's going to behave just like, how to say this, like the basic polynomial. So for example, x to the first power, that's linear, right? And so at this 0, it's acting very linear, meaning we know we're coming from below, we're just going to pass right through. When it's x squared, we know that's a parabola. So what that tells me is when I curl back down to hit this 0, I'm actually going to treat it kind of like a parabola right there, and I'm going to turn back up because the multiplicity was 2 was even. And so it always will behave like a little parabola at that 0, and it'll turn. And then we got to be back down here for this 0, and this one again is x to the first power, and so that's going to act linear and pass right through it. And I'm going to go down. I'm not saying it is linear here, but I'm saying just as if it was linear just for right here, it's going straight through. And so now everything fits. So we have to consider the multiplicity. And for some reason, there were a lot of students in Algebra 2 that really just got very confused by this concept. But it is just about whether it passes through that 0 or if it turns at that 0. And so we just have to pay attention. And it's not a multiplicity for the whole question. You have to answer it for each of the factors. So we have 3 different multiplicities to account for because I have 3 different factors. Okay, hope that makes sense. Let's do part C and D, and then we'll be done. All right, part C is already factored for us. So if I want the zeros, which is the main thing you were asked to find, someone's already done the hard work for me. So I know it's when negative 2x equals 0. I know it's when x plus 3 equals 0. And I know when it's when x minus 4 equals 0. I'm not answering it as x minus 4 cubed equals 0, because what this is really telling me is if I factored this all the way down, I've got an x plus 3 times an x plus 3, right? And so I already know when x plus 3 equals 0. I don't have to answer it twice. But that might come into play for something else. All right, so what are my zeros? My zeros are going to be 0, negative 3, and positive 4. And what is the multiplicity? X equals 0. This is x to the first power. So this is an odd multiplicity. The multiplicity we would say is 1. X equals negative 3. I'm not talking about the value. I'm talking about how many times is that factor there. X plus 3 is there twice. So that's even. It happens twice. And x equals 4 is a 0. And that one is odd. And it happens 3 times. Now, it's nice that it's factored for us. It helps us answer that question a lot easier, but it does disguise things a little bit more. And so I need to think about the degree of the function. So what I'm not asking you to do is multiply all this together to tell me what g of x is as a standard form parabola, polynomial. I don't want you to turn part C into something that looks like part D. What I want us to do is just get the information we need. So if I were to multiply this all out, okay, and I did x minus 4 cubed, I would do x minus 4 times x minus 4 and a bunch of other stuff, I would get x squared and some stuff, right? And then if I multiplied that by 1 more x minus 4, I would get a bunch of stuff, but I would have an x cubed and some other things, okay? So long story short, I can kind of make this easier on myself and just realize that I'm going to get an x cubed out of this. And then when I do, and I multiply it by this guy, which is going to have an x squared, I'm going to be up to 5, and then I have 6. So this is going to be some polynomial. Notice there's no leading coefficient, so it's 1 to the second, 1 to the third, but here is a negative 2. So this polynomial is going to be negative 2, x to the 6th, and a bunch of other stuff I don't care about. So my degree is even, and my leading coefficient is negative. So I'm going to go and put what I know. I have 0. I have a 0 out here at 4. I have a 0 here at negative 3. Odd at this one. Even at this one. Odd at this one. X to the 6, I'm going down because it's negative. So I'm coming up. At 0, it's odd. I'm passing through. At negative 3, it's even. So when I get here, I'm going to treat it like a parabola. I'm going to turn back. We said it was going down on both sides, and it matches. And this is our graph. Now, the one thing we could do to make it slightly better, and I'm not going to really make a big deal of this, but again, if we're striving for excellence, the graph here doesn't really act very linear. It's odd, so it does pass through, but what it does is it kind of behaves like an x cubed graph right here. So really, if I focus what it looks like here, it's actually going to come down just like an x cubed graph and kind of do a little thing like this, where it's going to kind of hit zero, like it's going to get horizontal briefly. So it's going to come in and it's going to come back out. So that's what's happening at that zero right there. Now, I'm not going to hold you to that. If you just show me it passes through, we're going to be good. But what's really going on is it's got this little guy right there. That's known as an inflection point, but that's more of a calculus term that we're not going to worry about too much here. All right, and then we've got part D. So, what do I know? Not a lot, right? I don't have very much information to go on. So, if I were to graph this, what do I know? I know about my end of behavior. I know my y-intercept, and that's about it. Because I don't know how to find the zeros of x to the fifth, at least not until later in the chapter. So I have this point, and I know I'm going up, and I know I'm going down. So really, there's not much for me to do on this question other than to maybe use my graphing calculator. And so let's take a look at what this graph would look like. Let me find my graphing calculator, pop it open. And doesn't need quite that much space. There we go. All right, so let's take a look here. Let's plug this in. Let's go to y equals. I'm going to clear that one out. And I'm going to go x to the fifth. Scroll out of there. Minus 3x to the third. Scroll out of the superscript. Minus x. I'm going to hit the squared button. Minus 4x. Minus 1. All right, I don't know what I graphed before. I don't know what this thing's going to look like. I don't know what window I need to see, so I'm just going to hit zoom 6 to start. That's not too bad. Okay, let's use our calculator for a couple of things. Let's use our calculator to find these zeros that it wants. So I can estimate, right? I can see I've got a 0 over here, but let's calculate it, okay? We're not going to use trace. We're not going to just walk our way over there, right? And just like, oh, what's it going to be, right? Oh, it's about that. We can do better. So remember, we have the calculate option. So we're going to go to second function, calculate. And you'll notice number 2 is a 0. So just like it did with minimum and maximum, it's going to ask us to go to the left side of where we think there's a 0. Now notice there are 3 zeros. So if I want to focus on this 0 right over here, right, then I better make sure I'm to the left of this 0, but not to the left of other zeros. So I'm to the left of that 0. I'm going to hit enter. I'm going to scroll over 1, which jumps me to the right already, but I'm going to go a little more just to, it evens off the screen, but I'm going to hit enter. You'll notice it still put the little window. But it does now ask for a guess. So it doesn't really want to guess. Remember, it just wants you to scroll back. Right now I'm right where I was when I ended, so I'm on that border. So I'm just going to tab one spot in. I'm going to hit enter. And so I've got a 0 at approximately x equals 2.115. If it doesn't specify a decimal amount in a question, let's go to 3 decimal places. Also, don't be alarmed with this y equals. This is scientific notation. It's saying 1.4 times 10 to the negative 12th, which is 0.000000, etc. 14. That's the calculator telling you it's 0, right? Based on the endpoints we picked on our left-right bounds, it calculated and has that little rounding error. All right, let's find another 0. Calculate. Number 2. And I'm going to scroll to the left of the next 0. or I could type in a number. All right, looks like I'm to the left. I'm going to hit enter. I'm going to scroll back to the right. I'm going to go back in between those, and it looks like I have a 0 at approximately 0.254 negative. And I appear to have one more. So I'm going to calculate my 0, and I'm going to jump over to the left of it, or I could type. Okay, so I'm to the left. I'm below it, right? So I'm going to move back, and I'm going to go 2 places just so I can have room to scroll back into the middle. And I get approximately negative 1.80861. All right, I want to do one last thing because I'm noticing a little something that we talked about here, right? Go back here. We talked about this little inflection point right there. I think I'm seeing something very similar right here, but I'm not sure. So I'm going to zoom in on that. So I'm going to go to zoom. I'm going to do a box zoom. I'm going to scroll over just to set the top corner of my box. It's going to set the top window corner. Now it's drawing a little line, and I'm going to go down, and I'm going to make that my window. All right, so at least at this zoom, I'm not really seeing what I thought I was seeing. I was just curious, and maybe I'm just zoomed in too far to see it. But it looked to me when I was zoomed out that we had a little wiggle either at the 0 or maybe at the intercept, but no big deal. So to sketch this, I know I'm at 2.115 or negative 1.8, negative 254, positive 2, and I'm getting kind of tired at this point, so I'm just kind of skipping the labeling part. I come down, I come up, miss it, and I come down, and I've got my graph. And that's pretty much what we saw, if I'm not mistaken. Zoom 6. Yep. And again, notice I'm way off on how far down I went, but I'm not too worried about that. Okay, I hope that helps, and we have some familiarity with our calculator, and let me know if you have any questions.